If it's working, then
I see, huh? And this is recording. And I just hide this. Now we just invest the mic. How the mic is on.
Try to motivate the people to start with management.
Let's start now. We are very honored to invite Professor Pagonabarraga Sorry.
No? Okay.
And then matter physics, University of Barcelona, to give it the first invited speak today. His topics is, I find extremely fascinating. It is microscopic motions that lead to large scale, phenomena. And I'm sure that the audience will be finding this very interesting. And another thing I was told this morning, the Spain winning against
France. Yeah.
So congrats.
Thank you. Okay, thank you very much for this nice introduction, and thank you, the organizers, for inviting me. It's really a pleasure to be back to this conference that I've been visiting for decades, not at any time, but I remember my first one in Boston. So now it's time in Zurich. So as was introduced, I will be talking about active complex fluids and the emergent behavior and multi-scale behavior that characterizes them, and why these are, from a methodological point of view, an interesting type of systems where the techniques and methodologies that we are listening to and we work with in this conference are appropriate and provide a very powerful tools to be able to tackle these problems. I like to start, for those of you, for some time I was the SICAM director in Lausanne here in Switzerland. I'm back in Barcelona, so I like to advertise that I'm back in Barcelona. This is the historic building, so I'm not working here. It's a nice view of the city. I also don't work here. I work close to the Camp Nou, again, football stadium. And as I said, I will be talking about active liquids. So very briefly, what is active matter and what are active systems? These are systems that are characterized, in very broad terms, by the fact that the relevant constituent units are able to convert energy into motion. And the source of energy can be very different. Obviously, most inspiration comes from nature, because all systems that are alive, animals, microorganisms, in a way metabolize food, converting energy, and then they can move around. So these are large scales, and this is like a very classical example, the starlings that fly together. And we want to understand, since the work in the mid-90s of Toner and Tu and Big Check, then there is this view from statistical physics of how we can understand this emerging behavior for these systems. But it can go down to scales. I will come back to this. This is motion inside the cell, or we can make them synthetically. These are colloids that are being excited through an electric field, and then they break symmetry, start moving around, and you can see how they are sort of like racing along together. Here is like a wave of these colors that come together. Also nowadays, and something that is really characteristic, I like to emphasize how different these systems are from equilibrium systems by, again, a classical example of a relatively old experiment where they fluorescently label bacteria. These are E. coli. And so where there is green, you have the E. coli, and then they put them in a box. And here in the middle, maybe you can sort of more or less see that there are like these wedges. So there is like a row of these wedges that are ordered so that the wider side is on the left, and then there is this funnel from left to right. And actually, they do not really interact very much. So they move around through a run and tumble. So on long scales, they diffuse essentially. But what you see is that they self-trap at the right-hand side of the box. If this could be an equilibrium system, it's not me. Okay, if it could be an equilibrium system, then the whole box should be uniformly green. So this tells you that by performing a motion that doesn't satisfy detailed balance, they can, at the end, when they collide with these wedges, actually the size of these traps is comparable to the typical run length of these bacteria, then they have a tendency to go towards it's easier for them, say, to move from the wider to the lower side. It's like a kind of entropic trap. And a complementary experiment is this one, in which you have now the bacteria here. So these are the bacteria. And then now you put a wheel, and again, this is asymmetric. So they come more frequently through one side than through the other, because again, detail balance is not satisfied. And then in this case, what they do is they can rectify motion. So in principle, you could extract work from here. So you feed the bacteria, and then you can get it rotate. Okay, so that's just a state where there is no driving. So in that sense, it's different from many other systems where we are used to drive them through forces externally of pressure gradients, electric fields, and so on. One important consequence, if we look now at scales where, like these bacteria that I was showing you are in a liquid medium, is that when they move, it's not only that they move around, they are not in vacuum, so they put the fluid in motion. Again, because there is no detail balance, there are net flows generated by these microorganisms, and these are flow fields that have been measured experimentally these are another type, these are Chlamydomonas, and you can see that if these organisms are micron size, flows are typically Stokes flow, Reynolds number is small, so flow fields decay algebraically, which leads to a strong hydrodynamic interactions between these microorganisms. And again, that plays a very important role. This is an example of a cell. This is a plant cell that is very long. It's like a centimeter long. And actually, I mean, here, the wall of the cell is covered by, you can see this elongated sort of stripes are microtubules. Molecular motors can move along them. As they move, they generate flow. And actually, that leads to a flow. I mean, what you see moving are like tracers of the flow. There is a flow taking place over the whole cell. So that is important because transporting elements by advection is much more efficient than by diffusion on long scales. So this has also, again, it's called cytoplasmatic streaming, and is now recognized as a relevant process to control metabolism in cells. So, and again, this comes because there are these motors that are moving along because they use ATP to move along these filaments, and then as they move, they generate flow. So these active flows are very important. And so what I will be, and up, I will skip this. Yes, and actually they are now leading to very complex time-dependent flows. And I can show you, let's see, I think this goes, yep, yes. So these are, again, active colloids, another type of active systems. In this case, these are colloidal particles that decompose oxygen peroxide, and by self-diffusive phoresis, they can move, and they sort of like move together. Again, this motion is controlled by flows that are generated by them. And you can see here examples of time-dependent flows in this microtubule kinesin complex. These are the micromotors, the molecular motors that I was telling you that form these structures in cell monolayers, bacterial suspensions, in quite a number of systems that move by either eating or by consuming a chemical. One can have quite long-range flow structures that usually are spatiotemporal dependent, so they are non-steady. And it is then also relevant to try to understand these structures, how they emerge, how they are linked to the activity, and how we can eventually control them. From a practical point of view, this is also like a new class of materials in which we understand how these processes take place, then opens up possibilities to manipulate matter at different scales, okay? So this is just to explain you that indeed, this is something that is relevant, is important. It has a biological and technological implications, but there is a lot to be understood in terms of what are the properties of these flows. So I will be looking at this using computer simulations models, and I will concentrate in one particular type of system that has become a reference because it contains many of these effects and because it corresponds to these microtubule suspensions that I refer very quickly. And so the basic idea, so maybe I can go back once. So as maybe I can go even back, if I can go back. No, how many times I have to click? Yep. So when I was talking about this system, I was saying that these are biological filaments on which there are motors, molecular motors, proteins that basically can attach to them. And when if there is ATP, by consuming the ATP, they can walk along. So basically you have a mixture of elongated filaments, these biopolymers, and the motors that attach to them that give rise to these active stresses. So these filaments then, because they are elongated, they have a liquid crystalline order, so they can form a liquid crystal. And this liquid crystal now is active, not because these polymers themselves propel, as I was showing you with the E. coli, but because the motors that attach to them generate active stresses against them. So you have an active stress. So it's like a system that in equilibrium will form liquid crystalline phases, but which is subject to stresses that are generated by these active elements. So I will then now look at this from this coarse-grained perspective. So I will not follow what the molecular motors are doing. I will simply say that effectively, the presence of these motors and the presence of the ATP generate the stresses. And then question is how these active stresses affect the ordering of these filaments. And this is actually, although I did not explain it in so much detail, what you could see, for example, in this image. So this image, here you see the texture by microscopy of these filaments. Again, the filaments that were in the walls of that cell, now they are extracted, and then you can make a suspension of these filaments. Filaments, they tend to come together. If there is black, there is no filaments. And then the motors moving around make these intricate structures that wouldn't be there in equilibrium. In equilibrium, they would tend to be aligned with defects that would coarsen and tend to disappear with time. So, can I go forward? I have to go through. Oh, yes, okay. So, how I will describe this in order to be able to reach the scales in which these filaments collectively can reorganize themselves and respond to these stresses, what I will do is I will take a coarse-grained approach where in the hydrodynamic limit, they will correspond to the two equations in the top that I don't reach. But the second one is like Navier-Stokes equation or momentum balance, where you have the convective derivative on the left, and then you have the divergence of the stress. And the stress, which is here, has three components. This would be like the what you would have for a Newtonian liquid. So that's the viscosity times gradient of velocity. But then because there is these filaments that tend to align, depending on how they align, then they will generate an elastic stress. And that is what they call passive. And then because there are the motors will generate also an active stress. These stresses due to the presence of the ATP and the motors moving on these filaments. And the simplest type of assumption is to say that this active stress is proportional to the degree of ordering, and now I define this Q, of these filaments, okay? Now, this tendency of the filaments to orient is then described in terms of this Q matrix. This Q is a matrix that tells us how much they align. And it's a matrix because if it could be a vector with a point, no, they could sort of like point together. But here, because the head and tail is the same, the way to say if they are aligned like that or they are aligned like that is characterized by a matrix Q. So Q is the way to characterize the degree of nematic ordering. And the fact of using this Q also has an overall amplitude. If we are in the isotropic phase, so there is no ordering, Q is 0, otherwise different from 0. So we can have an isotropic nematic transition, and we can then account for this cost of aligning. All this is encoded in this free energy, which is an elastic free energy, is not active, it's passive. This is the Jens free energy, where the terms that do not depend on gradient control the isotropic nematic transition. And this term K is the elasticity, is the cost of for the order parameter not to be completely aligned. So K is elastic, is the elastic response. And then the rest is whether we are isotropic or nematic. From this free energy, I can obtain the elastic stresses I was referring to. And also the very first row tells us how this order parameter changes in time. Again, the convective derivative, relaxation time H is like the derivative of the free energy. And then there is a coupling between Q and gradients. If there is a gradient of velocity, the shear, for example, then the nematic tends to align with it. And that's controlled in this term, okay? So this is the coarse grain approach that allows us to sort of be able to look at large structures without having really to follow what molecular models are doing in detail. And basically what we have been doing in order to be able to explore this systematically is to use a lattice-Boltzmann approach where we do not solve the Navier-Stokes equation for the velocity. We have a lattice-Boltzmann representation with a forcing that encodes this coupling through the stress tensor. And for the Q, we use a hybrid effective discretized way to equations to solve for this order parameter. Okay, so it's a hybrid scheme with lattice-Boltzmann and this representation for the Q vector. And that's what will allow us to really explore the complex temporal behavior of these systems. An important length scale that will come is the ratio between this cost to generate to deform elastically the nematic and the active amount of the amount of energy that we are forcing that we introduce through the activity defines a characteristic length that will feature later. And also technically speaking, depending on this coupling between the order parameter Q and the gradient, the nematic may tend to prefer to form a certain angle. If you think of a shear, they want to form a certain orientation with respect to shear, or it may prefer to tumble. So this parameter will tell us whether it's what is called nematic flow aligning or tumbling. This is related to Jeffrey response of molecules that are not isotropic. This is nothing to do with activity. It's just the coupling between how the distortion of an elastic medium responds to an applied shear. Okay, so this is the setup, and what we have been looking at now is at what happens when we have these systems. In reality, there is something that is well-known theory, which is that activity generates what is called a bending instability. If I have a perfectly aligned nematic and then I put a shear, activity will destabilize that nematic and form bands. And this is something that has been observed experimentally. It's quite clear that it's there generically. And you can see this is in a movie where start with a homogeneous nematic, active nematic, and then this instability starts developing. And that's the essential source for what I will be showing you, but then life becomes a bit more complicated. So it is known that this instability is controlled by a parameter A, that is the ratio between the system size and this active length that I was telling you. So if I take the system large enough, it will always be unstable. So you stabilize the nematic into a homogeneous phase by changing the system size. And as you now increase this parameter A, typically you will go through a sequence of instabilities. So here you see the magnitude of this vector Q, and you can form structures that are relatively ordered, but not homogeneous. And as you keep on increasing, it's a bit like a hydrodynamic instability where you have different phases, and then eventually you will end up in a turbulent state, in a spatiotemporal flows that are not characterized by any type of specific pattern. Now, I will be focusing on this in this final regime, so I will not describe how we go from the homogeneous to this spatiotemporal flow regime, something that still is not completely clear. But the understanding is that it will be controlled by this parameter A. What are the sequence of patterns, as for example, we know for Rayleigh-Taylor instability or for a Bénard instability still needs to be worked out. But at the end, once we are in a spatiotemporal flow, there we can characterize then the behavior by, as we would do in in turbulence, in inertial turbulence by, for example, looking at the kinetic energy spectrum. And the sort of like reference understanding is that this spectrum is quite rich. At high Q vectors, there is a Q to the -4, and at low Q vectors, there is this Q to the -1 that is related to active stresses and the flows that generate asymptotically at long scales. This has been obtained because it's a low Reynolds number. It's really solving the Stokes equation with finite different methods. But even if that's sort of like, I would say, one of the basic theoretical predictions, actually, I mean, experiments, these are experiments so this is a 2D system. These are experiments of a monolayer, quasi 2D. I mean, the point is that there are not many decades. Experiments are, I mean, depending how you want to look at them, you can say they confirm or they do not confirm. And there are even theories that rather than looking at the active nematic, they look at a set of stresslets of these points of stress in a homogeneous fluid. And they predict, so without elasticity, and they predict that this is not really true. So there is no Q to the -4, and at very low Qs, this should saturate to a plateau. So this Q to the -1 may be something intermediate. And okay, so here there are a few more decades, but all I want to say is that this is still not settled. What is really the right spectrum that you expect for these spatiotemporal flows? It's still a matter of debate. So in this context, we try to look at this with lattice Boltzmann simulations, and one of the nice things that we know is that allow us to cover decades. What I will show you, unfortunately, cannot cover so many decades, but we can go a little bit further than what had been done before. But we do that with the full Navier-Stokes equation, not with the Stokes equation. So what I will be showing you is typically what happens changing whether, something I forgot to mention, I was emphasizing, well, I will not go back to the equations. If you remember, the active stress is proportional to this amount of nematic ordering with a parameter alpha. Alpha tells you how strong this stress is. This alpha can be positive or negative. So this is the degree, and the sign is important because it means that these motors can generate stresses, active stresses, but the stress can be compressive or extensive. So you can have two types of stresses, and those two types of stresses actually give rise to different types of flow. So it's not just the degree of activity, the amount of stress, active stress that is generated by these motors, but the nature of the stress. If it's more compression or not, will also give rise to different types of flow. So what we have been looking is spanning parameters, trying to understand, look a bit on what are the spectra. So I will be showing you spectra for the elastic and the kinetic energy. And these are typically what we see. I mean, these are, again, for contractile and extensile, so positive and negative, this negative alpha and positive alpha. And if you look at the elastic spectrum, it's kind of like, so there is a characteristic wave vector, characteristic length associated to this energy cost that I was telling you, that will tell you where we are sort of like generating these elastic stresses. And this elastic deformation, this elastic energy will typically be converted into kinetic energy. That is how these flows are developed. Yeah. So activity generates elastic stress, and elastic energy is converted into kinetic energy. And a difference here is that while for contractile seems to be a relatively peaked value, so there is a characteristic wave vector where this energy is inputted in the system, that's not so obvious for the extensile case. If we look at the kinetic spectra, okay, again, so we can go, as I said, a little bit further than in previous studies, but still, we cannot really cover many enough decades to really say whether this is really K to the -4. I think it's never more, it's always a fraction of a decade. And for K to the -1, well, maybe there it's a bit better. But again, you remember there was this prediction, maybe it was leveling off. So could be that in some cases this is leveling off. So I would say in those cases, we can argue, still, I think one would need to go a bit further down here to really disentangle cases where this spectra is really k to the -1 or not. But something that we found is that now, this is by changing the parameters of the system and allowing on the size of the system. I mean, in some cases we went to, this is 2D, so we have lattice is up to 6,000 squared. On that scale, we allow a finite but small Reynolds number for the 5 or 10, finite but small. What we saw is that for extensile, and again, this is the same amount of activity, but one is contractile, so the sign of alpha is negative. So again, this was in our sort of quest to try to push parameters to see if we could see more clearly the regimes. What we end up is that for extensile, sometimes the power law changed into something that was more 5/3 or -3 asymptotically, which is reminiscent of 2D inertial turbulence. So basically here, and actually I show you in the inset, the kinetic energy is a function of time that is increasing. So actually in those cases, rather than trying to get into more clearly this final stage, what we found is, so these are again, the magnitude of the velocity for the contractile and extensiles, because there is this broader range of wave vectors in which elasticity is generated. Typically, flow structures or liquid structures are longer range. And actually, if rather than the velocity, we look at the vorticity, so we compute the vorticity of the flow, and here, what we saw in those cases is that these structures that I was showing you for the velocity actually feature more clearly in the vorticity, where you will see the appearance of essentially two vortices that become as large as system size. And that is basically what is known for inertial 2D turbulence. So actually what this is telling us is that for these extensile systems, it's not just that we are still not completely clear what is the asymptotic behavior in the absence of this scenario, but also that even if we at high Qs, we are at low Reynolds number and we have this transfer of energy from the elasticity to the kinetic energy due to the activity, there is a possibility now to generate an inverse cascade that will lead to an inertial turbulence. So this is a coexistence of active and inertial turbulence in 2D, okay? And maybe, I don't know how I'm doing in time. So that's just to say we cannot really resolve still the question of what are the spectra when there is only active spatiotemporal fluid motion. So people talk about active turbulence, but also the fact that we can have an interplay between active and inertial turbulence depending on the type of activity of these active systems, of these active pneumatics, okay? Maybe I can move to the second part, which is again, using the same sort of approach. I was showing you the behavior of 2D, and I was restricted to 2D because most of the studies were done in 2D, and those experiments that I referred to were really managing to have a monolayer of this active pneumatic and looking at it at 2D. But obviously, one also nice thing of this Lattice-Boltzmann approach is that we can easily go to 3D and also try to span and look at the behavior at larger scales in these other geometries. And here, rather than re-looking again at the spectra in 3 dimensions, I will now show you another type of analysis that we have done, which is the study of the defects. I haven't emphasized it very much, but when we have these spatiotemporal flows that I was showing you in the movies, if we look at the alignment of these microtubules, when they align to form this pneumatic order, typically there will be domains with defects. Those, in the experimental movies, they appear naturally. These are regimes or regions which are darker because typically there is less there are less microtubules actually. And it is known that in 2 dimensions, the defects that dominate are +1/2 and -1/2, which are dictated by the symmetry of the free energy. And because they are out of equilibrium, actually, the +1/2 propel, the -1/2 are more static. In equilibrium, they will form, but then with time, they will turn to coarsen. If a +1 and a -1 come close to each other, they annihilate, and then you have 2 defects less. And as a function of time, the number of defects decreases. It's a very slow process. But that's not true for these active nematics, because in the active nematics, the active stress is able to generate defects. So basically then defects annihilate, but then they are created. So in these spatiotemporal flows, if you would look and count the number of defects you have, there is an average density of defects. And let's see if I can, I think it's not in the right order, but if you look on the movie here on the right-hand side, they were tracking defects. The red are the +0.5 and the blue are the -0.5. They sort of like are generated. You can see that the reds are much more mobile. Maybe it's difficult to identify when 2 come close to each other, they will disappear. And then from time to time, there are new defects appearing. Okay, so that's again, nature of the steady state of this active system. And it's clear, that's what happens in 2D. In 3D, there were recent experiments by the group now in Santa Barbara, where they were able to sort of follow one defect and see what happens. And again, they 2 can merge and then annihilate, or I'm not sure if maybe they also managed to see the appearance of a defect. But in 3D, defects are of a different nature. Defects typically need to be closed on themselves in the absence of any walls. So we asked the question, can we try to also look at defects in 3D and try to understand how they behave? They are much complex than these 2D ones that by geometrical constraints have this very particular structure. So basically, we had to develop a code because now we have this Q field I was telling you. This matrix Q tells us locally the amount of nematic order. If we have a defect here in the core of the defect, there is no ordering. So we can identify a defect because the magnitude of Q goes to 0. So then basically what we did was to develop an algorithm in which from the map of this Q matrix, we could identify the core, and by a mathematical algorithm, try to convert that this is a field, to convert the area where the core, where this Q goes to 0, into essentially a 2D curve. So we have now 2D curves, and that allows us to track many of them, even if they are close. So you can see in this movie, it was a movie, if I can go back. Oops. So this is a very dynamical system where these long defects are moving around, they come, merge, reappear. So one needs a proper algorithm to be able to track hundreds of them as they move along. And that's basically what we did. So now with that, we can look at the statistics of these defects. Here they are again. So we could sort of like track them and then look at what's the distribution of these defects. These are always close, but of different lengths. LD is the length, the arc length of one of these defects. And you can see the probability is quite broad. So we can have relatively small, but also very large defects, okay? And actually that's like a power law distribution that we observe. So we could now characterize what is the nature of these defects. And actually, for example, we could compute the radius of gyration that they have as a function of their size. And for small ones, they actually grow linearly. Well, RG square goes with LD square. And then there is a typical crossover length where then they will become more like a random walk or a diffusive object. And also, if we look at the curvature, again, the curvature for small defects, this case is 1/L, which and it saturates to a characteristic length. Actually, if you look at a small one, this is a small one or a larger one, just that we can track. So smaller ones are really more like rings, and they tend to self-propel. When they are long enough, it's more like a very contorted object. So there is a characteristic, if you want, persistence length that depends on activity. And that defines a persistence that will separate. Small defects are ring-like, and large defects are much more like a random object, a random walk, okay? And actually, the movie that I was showing you for the experiments corresponds to experiments where they were able to track these smaller defects. tracking a large defect is much more difficult experimentally, okay? So also we could compute the velocity. So if they are small, they have characteristic velocity. Yeah, okay, I'll try to finish this. So, but something we realize is that actually, if we look at this cluster size distribution, there are two types of defects topologically in the system, because we can have what we call wrapping or non-wrapping. We can have defects that eventually will close on themselves, even if they go through periodic imaging, will come back to themselves. But there are others that do not need to come back to themselves. Okay, so these are the non-wrapping. And if you, I mean, this is in 3D. For me, it's a way to imagine what does it mean is if I could go to 2D, could be like the case in which we sort of like wrap around an arm of the donut, or we are in one side of the donut. Now, the blue one can be sort of like reduced to a point, while the red one cannot be. Yeah, this is an effect of the periodic boundaries, but generate these two types of defects. What is interesting is that if we look at the statistics of these two type of defects separately, as we increase activity, we are decreasing this length. The typical size of the wrapping ones decrease, so they become smaller, but the other ones become larger. So these two classes of defects behave differently with respect to activity, and the number that we have is also different. The non-wrapping ones, actually, it's always order 1. There are not many, but they are there. It doesn't mean we can have one of these at one time. It can break and become wrapping, and one that is wrapping can become non-wrapping. So they do not mean that there are two independent subclasses. This simply tells us that statistically they are always there. And if we look at the amount of volume that they occupy as a function of system size, the non-wrapping and wrapping, both of them occupy a finite amount. So as much as we could go, and again, that's an important case to use methods like lattice-Boltzmann, that we can sort of sample quite a variety of length scales, we can at least try to convince ourselves that over different sizes, this amount is there. It's not a finite size effect as far as we can say. So we can interpret them rather by, again, if we look at the cluster size distribution, at the defect size distribution, there is, as I said, so there is a maximum. Actually, this maximum is in this crossover region. There is this region for the rings here where they grow. And then afterwards, there is this decay. But when we look at the decay, there is finally this sort of like deviation. And actually, this corresponds to different system sizes. So as I increase system size, in a way, I'm recovering this algebraic branch, but there is a small fraction, but non-negligible in terms of the volume that occupies, that this is this few objects that are this non-wrapping, sorry, the ones that are sort of like topologically not connected to themselves. So this means that you could also think of this as a kind of a condensate that coexists with a regular fraction of a distribution of clusters. This part actually decays algebraically with a power 5/2, and this is consistent with a percolation, with percolating structure, with a Fisher exponent, where, I mean, the dimension of space is 3, the dimensionality of the object, because it's like the random walk, is 2, so this is a 5/2. So one can rationalize these two subsets of defects that coexist and that characterize the behavior of these active nematic spatiotemporal flows in 3 dimensions. Because it's late, I will skip the last part that was a bit different. I'll just simply mention this. I hope I've shown you that active turbulence, so these spatiotemporal flows, are really very rich in 2 dimensions, can lead to this coexistence of inertial and active turbulence. And still, I think the question about what's the right way, the asymptotic behavior of these scaling laws for these active flows that are not clear. And for 3D, we have started to develop methods that allows us to really follow the complex statistics of these ensembles of defects that are much richer than in 2D. And basically now we are starting looking at their dynamics and kinetic behavior. So this has been done with Cecilia Roray, a postdoc, when I was still at CICAM, Lino, who is in Barcelona, and Federico Toschi from Eindhoven. And thank you very much for your attention.
what you do, but general. And then we were doing phase separation. We always said there's no scaling if it doesn't extend over many orders of magnitude. The teaching is scaling equivalent to things that get stretch many factor of 5.
Mm-hmm.
How serious should we take that?
You mean because of the, yeah, no, that's what I mean. It's simply, I think that's still not clear to me. One would really need to do a much more serious study, varying parameters as we had done for the binary mixture to really be able to sample more decades. In a way, initially we were a bit naive trying to think, well, we can sort of like validate what has been said as usual. We realized that then it was even this other phenomenon of this coupling with inertia. So one needs to be, it's not just that one has to sample parameters, but one has to then be a bit more careful in how sampling to separate the two types of phenomena. But that's something that remains to be done to my, as far as I understand that's what I think is next, not to be able to extend by 2 or 3 orders of magnitude in Q space to try to see, because in some cases we see some bending, but it's very difficult to say whether this is intrinsic or not. I think that's really the question, whether the Stokes scenario or the stressless scenario is the valid one. That's something to be done. Yeah.
So, thinking about these wrapping and non-wrapping structures, in the video that you showed, it looks like the rings are always shrinking. Is
Yeah.
that the case, or you also see that? The second question relates to the position between wrapping and non-wrapping. So, if you have that, you should also have fragmentation of the non-wrapping ones. Do you
Yes.
see that?
Yes. Okay, we see everything that you said. So first part, rings. Actually, there is a nice argument that says that actually, if you take just one ring, you can estimate what is the elastic energy as a function of the radius, and you can also estimate what is the active energy or force. And this actually defines a characteristic length. Forgot to mention that. That's actually the length where we see the maximum, where we see the crossover from one to the other. So actually my understanding is that indeed, if you have the small rings by themselves will tend to shrink. Some of them then grow because of the dispersion and flows around them generated by the other defects. And in a way, those that manage to get there will become then this longer structure. So in a way, you could interpret the PDF that I was showing you with this maximum. You could think that there is like a branch of rings that is quite unstable, but those that manage to get is like they'll start fitting this algebraic decay that then will start growing. So yes, that is definitely a relevant length scale. That's what I call LA, and I haven't emphasized enough. The other question was about, yes, as I said, these are defects that break and form and coalesce. So we see fragmentation, they break apart, they form, they come together. So that's a continuous process that is going on among all of them. Yes.
You have just one more. Sorry. What about the fractal dimension of these lines of defects? Is that the random wall?
That's, yeah. So the ones that are long enough above that length scale, when we were looking at the radius of gyration is compatible with random walk. So it really, yeah. So it's in a way, so things go together, no? So there is this characteristic length that is a persistence length. That's what gives the ring its structure, which is controlled by the tendency of the elasticity to ring them. And once you are above that, then it's like a flexible object. It's like a flexible polymer that can be break, reform. It's always a ring topologically, but it's continuously then breaking up. So you could think at the end, that this power law is kind of also related to these processes by which they break and coalesce. So that's something we are thinking in computing as well. Yeah. If I make just sure, because I forgot to say that. So this is about this active pneumatics. There will be talks today, tomorrow and Friday by Rodrigo and and Nuno that will be building on this. So I think that's something you will be exposed along the conference. Yeah.
Thank you so much. And,
And then that works. Thank you. Yeah, I'm set. Yeah, thank you. So, thanks for this introduction. My name is Ljubomir Budinsky. I'm actually quantum algorithm developer researcher from the QuantScience company, which is based on Finland. What we are trying to do here is to move this CFD simulation a little bit further and try to do it on the quantum computers. Now, you probably heard about these quantum computers that they're actually now starting to be very rapidly developed by the several companies. Everything started something around 2019 when the IBM released the first 4-qubit machine. But now they are actually saying that in next few years, they will be publishing something around devices with approximately thousands of qubits. So what I'm saying in general, this is developing very rapidly. And what we're trying to do in the quant science is to find possible ways to do this, not only CFD, but the multi-physical simulation on the quantum computer. We are trying to develop the algorithm which can speed up extensively beyond any classical computation. Now, to do this, it's not easy, simply because the quantum algorithm, quantum device doesn't allow us much to do. But if there is a room, if there is a possibility to do some kind of computation, then the gain are the speeds that overcome or outperform any classical computation. So in today's talk, I will speak about what we did so far in the quant science. So I'm saying that we are the only quantum company that actually trying to do this currently. And we have, at least to my knowledge, very nice results. So I will present today what we did and why it's actually so difficult to develop the quantum algorithms. So before that, I will just, for those who are not familiar with quantum computing, quantum devices, I will just spend few minutes to explain how this in general works. And you probably immediately will see where the problem is coming from. Now, what are the actually devices, quantum devices? Quantum devices are the computers with the chips, and where the chip is actually built in such a way that can mimic small particles. Why small particles? Because the small particles obeys the rules of the quantum mechanics. Quantum mechanics as a field has several, as a system has several very interesting properties like superposition and entanglement. I will not go into details about these properties. I will just try to explain how this works and to some point address those things in order to be able to explain where this speed up coming from. So the devices, as I said, are the quantum, in general, quantum devices are the devices that obey the quantum mechanics properties. And the basic unit of the quantum devices is the qubit. Qubit is, you can think of as a simply bit, which can be zero in zero state, in one state, but in the quantum mechanics, it can also be in superposition. Which, if you look, if you listen to the mainstream, it can say that often say that we can have the 0 and 1 at the same time, which is true and it's not true. But in general, in contrast to the classical computation, where we can have 0 or 1, here we can have 0 and 1 at the same time. So the main unit is qubit, and if we look this property of superposition, this immediately said that we can, a quantum system can be in superposition state, which can be described simply as a linear combination of 0, 1. Superposition is, that's it. You can think about the superposition simply as a linear combination of the 0 bit and 1 bit. Now, in order to manipulate those kind of things, 0 and 1 has to be cast in some kind of mathematical description. So for us to be able to manipulate and calculate something. So the 0 state is simply described mathematically as a two-dimensional vector with this 1 and 0. 0, 1 is also the vector, basis vector, explained, described as a 0 two-dimensional vector with the 0 and 1. And the superposition you can imagine simply as a linear combination of those two. Now, the linear combination means that factors in those linear combinations are the complex numbers. So you can see here, C alpha times 0 plus beta times 1. I cannot reach, but you actually see. This is how we describe the quantum state of the qubit. So this is one qubit, which is in superposition, and it has two factors in front of that, which are complex number, and we call it as a probability amplitudes. For the qubit, that's it. It's pretty simple in that sense, but in this superposition property lies the possibility for exponential speed up, if you are able to extract. Now, once we have a qubit, which is bit, we need to have a tool to manipulate with them, which means that you have to have some kind of tool that can change this superposition. And if those tools, if we describe the qubit as a vector, those tools are nothing more than the two-dimensional matrices, which actually rotates and change those amplitudes in front of the states. So I'm feeling like I'm teaching the quantum mechanics, but in general, that's it. I'm trying to explain very broadly how this actually works. So you actually have a two-dimensional vector which describe the quantum state, and you have a two-dimensional matrix which simply rotates those things. And we often in quantum computing said this qubit can rotate in this sphere. So on North Pole, you have 0 state. On the South Pole, you have 1 state. And performing those matrix rotation, you actually rotate the qubit around the sphere. But what you actually are doing is just changing those amplitudes, nothing more. Now, once we have a tool, once we have a qubit, and once we have a tool, it's time to build something. It's time to try to put this qubit and to try to extract some information. And not only that, it's time to calculate something. Now, the one qubit as a one qubit is not interesting. What we need to do is to start stacking more qubits in order to build some system where we can calculate something. Now, when we add qubits, besides when we start adding qubits, the space, which is called Hilbert space, grows exponentially, which means that if one qubit is a two-dimensional vector, if we add one more to the quantum system, they are not add, there is a tensor product between them. So for the two-qubit system, we have a four-dimensional vector. For three-qubit system, we have eight-dimensional vector. And as you can see, as we add the qubits, the system grows exponentially, which immediately start thinking that simply with it 20, 40 qubits, 50 qubits, we get exponential space, very large space, which is one of the properties which is very appealing for the computation, because we all know that every numerical computational method actually suffers from this data grid expansion. And yes, every simulation that you did in lattice Boltzmann on whatever other computational method, you actually always want to expand the space. You always want to add more data, more the refinement of the grid and whatnot. So this expansion, this very large space immediately provides you with that. Now, the trick is here how to now, using those qubits and using those tools, how to manipulate those qubits in order to calculate something. Currently in the quantum computing community, there are several fields. They're already starting to getting nice results and nice speed up from this. It is quantum chemistry, quantum finance, quantum optimization problems. And one of them, luckily for us, is the computational fluid dynamics. Why? I will explain why. But before that, I will just show one simple algorithm just for you to get the idea how this actually looks. Because for someone who is dealing the classical computation, even lattice Boltzmann and any kind of different computational, this is not intuitive. This doesn't look nice. But what we have here is some simple algorithm. This does nothing reasonable, nothing meaningful. It just shows how these actually things works. So we have a 3 qubits, which is eight-dimensional state. You can imagine it as an eight-dimensional vector. This is the initial state. Then we apply 3 gates on each qubit, which means that I simply take the qubit and rotate around the sphere and obtaining the superposition for each qubit. So after the first sequence of the H gates, which is called the Hadamard gate, I will have all 3 qubits in the superposition. So if you look the qubits separately, you will have two-dimensional vector, two-dimensional vector, two-dimensional vector with the equal superposition, which means that both coefficients are the same. But this entire quantum system will be in the product states, which means you will have the eight-dimensional vector, and each number will be 1/4, which is tensor product of those 3. What I'm saying is that when you stack the qubits along one of each other, the resulting quantum state is not like you add those vectors. The resulting quantum state is obtained as a tensor product of those vectors. Now, if I add 4, I will get the state vector of the 16th element. Those gates, Hadamard gates, are the 1-qubit gates. And all the gates that we have are pretty much nothing more than the rotations. Beside that 1-qubit gate, we also have the 2-qubit gates. The 2-qubit gates are mostly the gates that are controlled on 1 qubit and perform something on the other qubit. So this particular is the control phase gate, which says if the second qubit in the state 1, I will introduce the phase in the first qubit. And that's it. In general, real devices accept only those 2 types of gates. 1-qubit gate and 1 2-qubit gate, which is control X gate, nothing more. But when we write the algorithm we can have multi-control gates, which means that I can say if the third qubit is state 0 and the second qubit is state 1, let's do something on the first qubit. But when we apply those kind of things on the real device, we need to first decompose everything on the 1 and 2 qubit gates. So in general, that's it. We have a qubit, we have a tool to rotate those kind of qubits, and now it's time to see, is it possible to calculate something? The essence of the quantum computing are primarily two things: superposition and entanglement. Yeah, it's look like mainstream talk, but in general, after my experience of 2-3 years developing those kind of algorithms, I strongly believe that what we do is actually attacking those two quantum mechanical properties to gain the speeds, to get exponential speeds. I will explain what the exponential speeds are. But there is strength of the quantum computing in this superposition. Now, also, before I'm entering the computational fluid dynamics in general, I just explained what the current state of the quantum computing in terms of computational fluid dynamics and in general. So we have in general two directions. First directions is what we call the quantum linear solvers. So for the quantum linear solvers, in order to, for example, calculate something on the quantum device, you have differential equation, any of the kind. You perform some kind of finite difference, finite value method. What you end up every time is some kind of system of equations, algebraic equations, yeah, linear or non-linear. Now, if they are linear, there are actually two already algorithms on the quantum which promise, and it's confirmed, they provide the exponential speedup. This is the famous HHL algorithm. This algorithm actually, when you start calculating the system linear equation on the HHL algorithm, you will get the speeds that any kind of classical computation cannot. So it outperforms any classical computation. It is logarithmic dependency between the data that you operate and the states, between the data that you operate and the operations that you're applying. Now, what I'm saying often when I want to explain what is the quantum computing is simply like this. If you have 5 jobs to do, central processing unit chip will start doing one after another. This is the sequential. In parallel terms, if you cast this on the GPUs, you will simply divide and parallelize, but the amount of work is the same. Yeah? Now, in the quantum computing, you will have one processor doing all the 5 tasks in parallel. This is actually how to picture a quantum computing. This cannot be done classically anyway. Yeah? So, this HH algorithm already said that he has ability, and it is. But since this algorithm operates, how it actually calculates the system of equations is doing inversion of the matrices. And when you're doing the inversion of the matrices, then you inherit all the problems that follows, like condition number, like the sparsicity of the matrix. So that means that matrix that you actually solve has to have particular properties in order to get the speeds. It has to be sparse. It has to have some kind of proper configuration. So yeah, it provides the exponential speedup, but it has a limitation. The second algorithm is the variational algorithm. It is optimization algorithm, which means that you solve the linear system of equations by trying to find the minimum of the cost function. This is the hybrid method, which means that some part is done on the classical and some part is done on the quantum. And those are only two currently available procedures they claim that have the exponential speedup. Even in my practice, I never saw that any of these algorithms provide some kind of simulation of any kind of problem. And I try to do this, for example, for simple 8x8 matrix problems, some kind of heat temperature, it's not, and it cannot solve because it has so many problems with it. But in theory, when you read the article, you will see that it provides the exponential speedup. And it is. But what we are interested in the quant science, not only in theory, what we want to do, we already want to build the algorithm that actually can run and that can actually solve something. So the second thing, second second direction on the available algorithms are the lattice-based methods. So actually what we discovered that when you look the lattice gas automata and lattice Boltzmann method, in the structure of the method, pretty much aligns with the quantum system. How? I will explain in detail. But in general, when you look the lattice Boltzmann method and when you look the quantum system, you will pretty quickly you will find similarities. This also stands for the lattice gas automata. So when I started researching this 2-3 years ago, I immediately started to implement the lattice Boltzmann on the quantum. And on some point, I turned my attention also to the lattice gas automata. So what we are currently doing in quantum, we're doing in parallel. So now I will explain first the lattice gas automata, what we did for the lattice gas automata, and after that I will explain what we did for the lattice Boltzmann. But currently the lattice Boltzmann is the only method that can be run on the quantum algorithms that actually has proven to provide the speedups, and we also managed to simulate some real use cases. It's simple, but it's real cases. So here's the lattice gas automata, some preliminary, some short introduction, but I'm thinking that it is for this auditorium, it's not necessary to explain what is the lattice gas automata. And it is something that is pretty old method, and it's for problem with the lattice gas automata for us is that it's not very well researched, because the researchers who started with lattice gas automata moved pretty quickly to lattice Boltzmann. So this is something that left behind. But what we know, we have several different models, HPP, FHP 1, 2, and 3. But why we actually did choose the lattice gas automata model? When you look the lattice gas automata model and we want to solve the quantum algorithm, quantum devices, it has some very nice properties. First property is binary representation. So you have a channels where the 0 is 1, and it's pretty simple. But from the quantum computation theory, second thing is the unitary collision operator. So when you look the lattice gas automata operator, it's pretty simple. But from the quantum side, every operation that you're doing on the quantum system has to be unitary. So this is the restriction, which means that I cannot apply any kind of matrix to rotate those qubits. I can apply only unitary matrix, because the unitary matrices preserve the probabilities of the quantum system. This is one of the postulates of the quantum mechanics. And apparently lattice gas automata has the collision operator, which is unitary, which is perfect for us. Second, besides the collision operator, I didn't write this, but the same thing goes with the propagation part. When you look the propagation part, it is also unitary. So if you look the lattice gas automata, it has 2 steps, collision and propagation, and both of the unitaries, which is perfect for the quantum system. The second thing is that quantum system operates and obeys linear structure. So the entire quantum system is linear, which means that if you have a linear tool, it's very difficult to calculate the nonlinearities. This is something that Professor Sauer will speak on Friday. But on the lattice gas automata, these nonlinearities come naturally, which is, again, one of the ways solving nonlinearities on the quantum system. So, and the last thing, which is also very appealing for the quantum, is this lattice gas automata noise. We know that the lattice gas automata are noisy models. And also new devices, these devices that we have now, quantum devices, are also noisy. which means that those qubits doesn't behave like we wanted to behave. They have some kind of errors. They have some kind of errors in the qubit system. They have errors in the quantum gates. They have errors when the device entangles with the environment. It's not some kind of classical property, it's quantum mechanic property. Entanglement, this is like, probably aware of this entanglement and the Einstein and the glove and whatnot. But what the problem is with the current devices is they very quickly entangle with the environment. Which means when you try to rotate the qubit, if it's entangled with the environment, he will not listen to you. He will listen to the environment. This is why all those devices are stacked in the containers, in the fridge. That has to be cooled down to the absolute zero in order to eliminate those outside imperfections. But lattice gas automata being the noisy one, also we have an idea that maybe the noise coming from the lattice gas automata and the noise coming from the device can be somehow combined. So what we did next, okay, we decided, okay, let's build the algorithm. This algorithm is actually for 2D HPP model. And this is how it looks when you translate the lattice gas automata HPP model to the quantum device. This first part is the collision part. So the first block, blue block, is something routine that we use from the IBM Qiskit. It is simply subroutine that initialize the system on the lattice gas automata. So you actually put some particles somewhere, depending on what you want to simulate. The second part is the collision part. So these 2, 4, 6, 8 multi-control gates perform the collision part. So this is everything that you need to do in order to perform the collision in the lattice gas automata. So you see, those are multi-control gates. They do something to this qubit, they rotate the qubit, and what you get at the end of the collision is collision step. Now, I know this is not intuitive, but this is how the quantum algorithm works. After that, there is a part which is simply transform. It's not so important for the lattice gas automata. What is more important is the collision part. Now, what I want to emphasize this. Okay, let me just show. And this is the algorithm who actually performs the propagation part. Again, you will see the bunch of gates and whatnot, but this is what we actually developed in the quant science. This is new optimized version of the propagation part, but let's not think about this now. What I want to say, what I want to emphasize here is that if you look at the collision part, those are qubits. We have some kind of states. Imagine like lattice gas automata, you start doing the classical lattice gas automata. In order to perform the collision, you need to go on each lattice site and perform the collision, yeah? Now, in the quantum, like I said, we first bring everything in the superposition. And what we did, we only need to perform the collision on one lattice site. And immediately collision is performed on entire space. So there is no need to go and perform the collision on each lattice site. And this is the first time when you actually see the gain, the speed up of the quantum computing. The superposition, you bring everything in superposition, you bring everything active, every state active, and you just perform on one state, and immediately collision is performed on all other states. Which means also, if I want to expand the state, my space, sorry, not the state, the space, adding 50 more qubits, adding thousands of qubits, I will not have to change collision part at all. Which means we are pretty efficient in that sense. But imagine if you want to perform the lattice gas automata on millions and millions particles. The computation will start to become very expensive. But here is not. I don't have to do anything. So this is a really power of the quantum computing. So in this case, collision part scales with the data constant, which means that if you add the data, you don't have to add any more resources. Yeah. Now, the same thing is for the propagation part, but I'm saying this is new optimist propagation part. I will explain this later. This is something that we developed in the quant science. It's an algorithm that performs the same thing, which means that if you add more qubits, if you add more lattice sites, you only have to add one more gate to this algorithm in order to cover this huge space. And this is all because the superposition and entanglement property of the quantum mechanics. So as you can see here, we actually succeeded in extracting those speeds from the quantum properties of the system and put it into lattice gas automata. So entire time step is done on the quantum. This is the result for the different time steps for the 1D lattice gas automata. You see the two lines. The red line is the classical simulation, and the blue line is the quantum. So we have simply 1D lattice gas automata. We put some kind of hill as the initial condition and let it evolve. And you can see the comparison between. This is done on the simulator, not on a real device. Because in order to develop the algorithm, in order to check the algorithm that works, I cannot simulate on the real device because the device has the errors. So there is a simulators that actually simulates real quantum computers. So we get very nice results, and we actually proven that the lattice gas automata, one-step lattice gas automata provides the exponential speedup, which means in general, if you increase the number of lattice sites in the classical computation, for each lattice site, you have to perform additional computation. Here, you don't have to do anything. So this actually proves that the lattice gas automata has the exponential speedup. Also, we did try on the devices, real devices with the noise, to see how this noise from the lattice gas automata and real device combine. So there is a different level of the noise for each device. So we tested on 3 different levels. So you can see with the low level noise on the real device, we also get real nice results. Even with the mid, I don't want to say what kind of, that doesn't matter. So, but we have the lowest noise is 800 shots and the highest noise. It doesn't matter in the general set. What is matter is that for the low and the mid level of the noise on the real device, we can have very nice results, which means that the noise from the lattice coming from the lattice gas automata and noise coming from the devices somehow combine, and you can get really nice results. And this is also done, just to be sure, to be clear, on very small lattice, 16 lattice sites. Not because I'm lazy and I don't want to do a little bit bigger, but because the quantum devices doesn't currently provide us ability to simulate some large algorithms. But they will. Now, after this, we try to simulate some real case scenario using the lattice gas automata model. And what we did, we have been very ambitious, and we tried to simulate the airfoil. So the first is the classical airfoil simulation on the lattice gas automata. So you have average velocity, pressure, and whatnot. Then, in order to be able to simulate something like this on the quantum, I cannot use this grid 300 by 200 because it's too big for the current devices. So I have to shrink. If you shrink, you get something like this, which is very simple, 30 by 20. But it's still airfoil. At least it looked like. Now, this is the simulation again from the classical, and this is from the quantum. So you can see that we can simulate even a little bit complicated things. If I have ability to simulate bigger space, these two examples confirm that if I have the ability to simulate bigger space, I will get the same results on the quantum like this. This just shows that the results that coming from the quantum are the same like that coming from the classical. But with one difference. This provides the exponential speed up, this doesn't. Now, logical step after this, if you look at those two steps, collision and propagation, logical step is now, is it possible to do the same thing with the lattice-Boltzmann? Because lattice-Boltzmann has all the same properties, of course, similar properties, at least some parts. Okay, again, I don't think that this should be explained. Now, this is how we started. I started to develop the quantum algorithm and said, okay, the lattice-Boltzmann has three steps: collision, propagation, and calculation of the macroscopic values. So from the lattice gas automata, we saw that the collision is unitary. It can be applied, but the collision on the lattice-Boltzmann is not the collision on the lattice gas automata. They are different. Now, but the second part, the propagation, is the same thing. So I decomposed and developed some general structure of how this algorithm should look like. We have first encoding part, which initialized the entire state lattice-Boltzmann. So there is this part actually introduced the distribution function, initial distribution function from the lattice-Boltzmann into the quantum devices. So I rotate those qubits in such a way so that amplitudes of the quantum states, those amplitudes, store the information of the distribution function. This is done here. The second step is the collision, following simply the lattice-Boltzmann, then the propagation, then the macroscopic, and then the boundary. I don't want to get into details, but in general, you saw that how it looked like I will just explain the crucial parts. So the encoding initializes the entire state. So putting quantum computer to accept this distribution function. Then we perform the collision and perform the propagation. Now, without going into any kind of details, I will explain how this algorithm actually looks for the simple case. But what we have developed now in the quant science is the 1D advection diffusion quantum lattice-Boltzmann, 2D advection diffusion lattice-Boltzmann, 2D Navier-Stokes quantum lattice-Boltzmann, and I will explain the latest research. We did combine Navier-Stokes and the temperature. But this is not important. What is important here in the quantum computing is not only that you calculate something. It's important to extract those speeds, exponential speeds, because if you cannot do this, the quantum computer will not provide any meaningful results, in that sense that why you should do doing on quantum when you can do it on the classical. So the main question is it possible to run those kind of simulation on the quantum, but to gain those exponential speeds? From the lattice gas automata, we see that there is a room for this, but the lattice-Boltzmann is a little bit different. Now, this is what we have now, and I will just shortly explain how this 1D advection diffusion quantum algorithm look like. So here's the encoding. So just to be clear, this is the linear problem. This is not the nonlinear. This is the linear advection diffusion, because we have a quantum which is linear system. Nonlinearity is solved differently. It's completely different story, and this Professor Sauer will explain this. First, we encode, which means that we input initial condition in the quantum system. Then we have the collision part. You have two Hadamard gates, and you have two control gates. This, when you see the collision part, is actually look like this. C1 gate is simply decomposed. You actually have a bunch of gates, control gates, which does nothing more than rotates the qubits. like I explained in first. And after this step, you actually perform the collision on the 1D advection diffusion equation. And what is more importantly, again, if I add 1,000,000 qubits below, I will not have to change at all this part of the algorithm. It simply stays the same. You can imagine like I perform the collision on one lattice site and immediately perform the collision on all lattice sites. If you have the billion lattice sites, you will perform the collision on the billion lattice sites. Yeah? Then we have a propagation. Since we have a 1D advection diffusion model, we have the first one, propagation performs right propagation, and the second is left, because we have two velocities, yeah? So this actually performed the propagation. And the second part, the third part actually calculate the macroscopic values. Now, all three parts are behaving pretty much the same. In contrast, when I start to expand the space. Only thing that I have to do is to add some small number of gates to the propagation part, but I will still get the exponential speedup. Now, after this, we start, okay, let me just explain. This is how the entire algorithm looks when we transform in the Qiskit, which is a framework from the IBM real device. This is called, the software that is called Qiskit, and it's written in Python, and you do use it to write the algorithm, and this is how it looks like. You see simply a bunch of gates. Again, the pink one is the initial part. The second part is until this Hadamard gate, this blue gate. This is the collision. Then we have a left part between those two barriers. The second is the right barrier, and we measure at the end. I will not go into measurement. It's a tricky part. But in general, if you look the one-time step, this is how it operates. We tested this algorithm on one simple case, Gaussian hill. We have comparison between the analytical and results from the quantum, and you see we get the perfect results. Then we also run it on the real device because those things are run on the simulator. But here we are running on the real devices, just one time step. And you still see that this dash line is what we need to get, and the red line is what the device gets, what the device provides. So you will see there is problems, but this is the problem with the devices. And this is actually done 2 years ago. So if we repeat this again, we'll for sure get much better results. But the next thing, this is for the 2D advection diffusion equation. When you go to the 2D advection diffusion equation, only two things that you need to do is a little bit more transform the collision part. You see in the 1D advection diffusion, we have a two velocities, two distribution functions. So we have two gates. We each perform the collision for separate distribution function. In 2D advection diffusion, we have 5 distribution functions, 4 velocities, and 1 resting particle. So this collision part, you see the 5 gates, and each gate perform the collision. And again, if I add more qubits, I will not need to change this algorithm at all. Now, since I have 4 directions, I need to perform twice. So here are the 4. Here are the 4 algorithms. This perform right, this perform propagation in right direction, the left direction, up direction, and down direction. Doesn't matter which, because it's called right or left, but it's... Now, after that, you see here the algorithm right in the Qiskit. It is written as a box because if you expand it, you will get many gates, and it doesn't look nice. But what we did, we tested again on the 2D at Gaussian hill, and we test that algorithm against the analytical solution and against the classical. So it's simple problem. 2D advection diffusion Gaussian hill, you perform some evolution, and those are results. And again, you will see that you see the algorithm performs very nicely. Now, after that, we move to the Navier-Stokes equations. Since Navier-Stokes equations are a little bit tricky because this is a nonlinear part, nonlinear problem. Nonlinearities are solved a little bit differently. But what this algorithm is doing is calculating the Navier-Stokes using the Lattice-Boltzmann equation, but in the stream vorticity approach, which means that I'm solving two Lattice-Boltzmann equations, one for the stream and one for the vorticity, where the nonlinear part is solved classically. So you can call it like a hybrid model. But what is interesting here is that now, in this algorithm, I can solve two Lattice-Boltzmann equations. And the question that arises, is it possible to solve even those two equations in parallel? Like I did for the collision, is it possible to bring everything in superposition and simply just run it one algorithm, one Lattice-Boltzmann equation, and it will solve for this substate, for this substate, for this substate, meaning that you are solving two Lattice-Boltzmann equations in parallel. So this is the question that arises from here. And apparently it is possible. Now, again, I will just explain. So this is first the collision part, and you will see now that here we have two advection diffusion equations, each having the four velocities. So the propagation part for the first diffusion equation is here. We have four propagations, and for the other equation is here. Yeah? Now, in the quantum, doesn't make sense if you perform the propagation once for some substate. You can expect that you can do it in the same manner, at the same time, at the same price, for all the substates. Which means there must be a way to replace those two algorithms with only one. I don't know if I'm, at least I'm trying to be, to explain. But in general, you can imagine like doing the propagation for two Boltzmann equations, just running the one propagation algorithm. This is the strength of the superposition. Now, is it possible? Yeah, it's possible. So this is what we did as a simulation. It doesn't matter too much, but what we want to explain, what I want to explain now, after performing all those things, some question arise. Can we optimize those things? And one thing that I can look at is that now I can start even improve all the parts of the algorithm. So where is the room? What we can improve? We can improve the shift algorithm, which we did, I will show you. Then how to connect several time steps when I perform one time step on the quantum device. After each time step, I have to measure. This is how the devices work. But there is a way to simply run entire algorithm on the device and just measure at the end. It's a little bit tricky, but it can be done. We did that for the simple cases, so we confirmed that it can be done. Now, what we did here is first attack this shift problem, because we saw that in the shift algorithm, there is a room for addition of the optimization. And what you actually see here is the algorithm that performs shifts in all four directions at the same time. So I'm bringing all distribution function in the superposition, perform this algorithm, and he will perform the shift in all different directions at the same time. And again, what is more interesting, if I start adding the qubits, expand the space, I will not need to change this just a little bit. But what is new here is that we have an algorithm that can perform shift at the same time. This is something that you cannot do in the classical. You can say I can perform shift in parallel way, but this is not the same thing. Even if you do it in parallel, you separate on the GPU, you still, when you expand the qubits, when you expand the space, you need to add more GPUs. Yeah? But here, you don't have to do anything. So this algorithm actually provides now. Now, the question is it possible now, when I'm already doing the propagation for those 4 directions, is it possible when I add more lattice-Boltzmann equation to again perform the propagation for all those Boltzmann equations with this algorithm? Nothing to change. And actually it is. So doing the multiphysics simulation using the lattice-Boltzmann in the quantum, meaning that I'm solving different lattice-Boltzmann equations. They are coupled somehow, but it doesn't matter. But if we concentrate on the propagation part, it means that with this algorithm, you can perform as many propagations as you want, just running this one algorithm. So this is a true power of the quantum mechanics and the true power of quantum computation. So we are tolerant completely on expanding the space. I don't care about the expanding the space. I'm just running this thing, and it will expand, it will perform everything. So I'm constantly talking about the exponential speedup, and this is how this actually looks. Okay, this is the qubits, but when I said the exponential speedup, what I mean is the difference, is the actually relations between the data that you operate and the operations that you, the data that you operate and work that you are putting to operate on the data. Meaning that in classical, if you add more lattice sites, you will need to add more work, more process to process those lattice Boltzmann, those lattice sites. But in the quantum, this line is logarithmical. Okay, those are qubits, but the qubits are not right way to but if you want to get the state of the quantum, you just go to the power of number of qubits, and you will get the dimension of the state. Someone said that, for example, to the power of 50, you will get the number of all the atoms in the entire universe. So just 50 qubits, I will get the Hilbert space so big, which is like number of atoms in all the universe. So you can imagine what we can do with only 50 qubits. It's huge space. Now, what I show here is the possibility, numerous possibility to advance to get this exponential speedup. And the last thing that we did is to simulate airfoil on the quantum combined with the temperature. So this is actual simulation of the airfoil in the quantum device, where we combined Navier-Stokes and the temperature. And we also confirm here that we can do propagation and a certain part of the collision at the same time, which means that I can add 50 lattice Boltzmann equations on top of this, and I will not change my algorithm at all. So this is the latest. This is actually from the BMW challenge. Okay,
Yeah, 5 minutes including the questions.
yeah, okay. Those are just problems that we had. This is just the start, but we actually prove that we are on the right way. We are on the right track. What we're currently developing now is the algorithm for the acoustics, which will be probably released by the end of the year as the first quantum product for the CFD acoustic, which will fully be running on the quantum devices. So, and of course, there are problems like non-linearities, but apparently I don't have time to speak about this. But as I said, for those who are interested in this, Professor Sauer will speak on the Friday about the problems like nonlinearities, particularly the nonlinearities, because nonlinearity is a pretty big problem in the quantum computing. So thank you for your attention.
Very impressive. I'm really excited to hear it. One thing is that in the early, at the beginning of the 30 years or 40 years ago, when people started thinking about LGA, that wasn't automata, was for the motivation of direct simulation of the turbulence. All right, or even the Laddy-Boltzmann or other conventional method, that is still considered prohibitive for the foreseeable future. But in the quantum computing, that really makes it more feasible.
Yeah, exactly.
So the LGA, like the early pioneers,
Yeah.
kind of faded away.
Yeah.
Because of three major criticisms. The first criticism is the noise.
Yeah.
Second criticism is the
Yeah.
Third one is the complication of the collision process that in the end result in very large viscosity.
Yeah.
So these three are the major obstacles. But as time goes, actually we know how to resolve the second and third problems. The expensive of the collision operator is still a problem, but you can do it with quantum computing to reduce, to bypass this time consumption.
Yeah.
And the time cost issue. And you can really operate, the collision process is much better than the Laddy-Boltzmann BGK or other equivalent. That you just operating collisions.
Yeah.
And that naturally satisfies the H theorems and many things.
Yeah. Yeah. Yeah.
But the statistical knowledge requires a huge.
Exactly.
Huge average.
Yeah, exactly.
And then you say,
Now we have this.
expansion of
Exactly. Exactly.
that really is exciting. Now my question is that what is obstacle that prevent quantum computing to go? You're solving a small system, right? And you are doing this estimation of potential things mostly from a theoretical.
Yeah. 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 Yeah, no, this is a $1 million question because what is preventing is the problem with the real device technology. So the real device technology, like the lattice gas automata, is noise. Also, the devices are noise, which means that it prevents you to run very large algorithms for a significant time. So the depth of the algorithm, meaning of those number of gates, you can just apply a limited number. For example, in order to perform any kind of simulation, some on real device, which is reasonable to get nice results, you need to have depth around 200, which is for the lattice Boltzmann. If I decompose the entire thing, I will get something around 1,000. So this is the first thing. The second thing, that qubit as a qubit is still unstable. When I said it has a zero state, if you put the zero state in the device, after some time, he will start moving. So imperfection of real devices in the current state are preventing us to do this. But if I have real, which is called fault-tolerant devices, then there is no obstacle to running this and to get there. But as I said, day by day, they really start very improving significantly because many companies are developing different types of the computers. Not the IBM uses this superconductive, but there is a photon and whatnot. So there is different technologies. So once when we have this, and I really expect this some time next 7, 8, 10 years, we will really have fault-tolerant devices. So this is actually what prevents me. to running this on the algorithm. Not the algorithm itself, but the imperfection of the devices.
I happen to read your papers as well. So I think there is something that I want to ask that is in the paper, but you haven't really discussed so much, which I agree actually in the paper, which is often in CFD, we're actually interested to know the time-dependent solution of the problem. And then you start getting into the problem, and I think this is really expensive. And then it seems this actually kills the exponential advantage. So I'm just wondering if you could comment on that, because I don't know if you've solved it, that would be great if you have. But to me, this seems to be a major problem.
Yeah. This is the problem. The problem is that what I show here is just one time step, which means you start and you end after time step, you need to measure. How the real device works is that at the end of the real device, you measure those qubits. Doesn't matter how, you just measure. And if you measure, you destroy the exponential speedup. But there is two things. First thing is what we developed in the quant science is to measure after entire simulation. So what I'm trying to do is connect time steps without the measuring. If I succeed this, there will still be exponential speedup. It's not destroyed. It is actually developed already for the simple linear cases. We managed to connect several time steps for the 2D advection diffusion equations. So I'm running 50 time steps on the quantum algorithm on the simulator and measure only at the end. So it's possible. The second thing is that often we don't need to measure every property of the field, flow field. Maybe we are interested in just some kind of forces around the airfoil. So what I can do is simulate those things and applying the operator, which is standard procedure in the quantum mechanics, expectation values, and extract only these forces. But in general, if you have a linear problem, you can connect those time steps and the exponential speedup will not be destroyed. Because the only thing that you get is the depth of the algorithm. But this doesn't destroy the exponential speedup. Because even in the classical, after each time step, you still have to again perform the computations, yeah? Still, but in the quantum, if I combine the several time steps, actually it appears that some gates can even be canceled. So by connecting the time step, I can additionally optimize my entire algorithm. But just to be sure, this is a research. We just started to enter this field. We don't even know the possibilities, but how it looks now, it looks like that if one time if we have some kind of that model that can simulate something on the quantum, it will be probably lattice-Boltzmann or the lattice gas automata. For example, the lattice gas automata naturally solve these nonlinearities simply by using the collision. So this is, but of course there is a problem. It's not everything perfect, but yeah.
Okay, thank you, speaker again. Thank you.
Thank you.